The thickness of the cohesive zone, CZ, in a blast furnace is a critical operational parameter, as it significantly influences gas flow, burden descent, reduction efficiency, and overall productivity. The cohesive zone is the region where iron-bearing materials soften and melt, forming a plastic or semi-solid mass. Its thickness refers to the vertical distance between the softening start temperature and the melting or dripping temperature within the burden column. A thinner cohesive zone is generally more desirable because it offers better gas permeability, reduces pressure drop across the furnace, allows more efficient reduction and smoother burden descent. The thickness of the cohesive zone depends on a variety of factors, primarily related to raw materials, furnace design, and operating conditions. Key factors affecting cohesive zone thickness. Softening melting characteristics of burden materials. The most direct factor influencing CZ thickness is the softening and melting behavior of iron-bearing materials, sinter pellets, lump ore. Parameters. Softening start temperature, Ts. Melting or dripping temperature, Tm. Delta T is equals to Tm minus Ts determines CZ thickness. Influencing factors. Chemical composition, higher levels of SiO2, Al2O3, or alkalis lower the melting point, potentially reducing CZ thickness. Basicity, CaO by SiO2 ratio affects slag formation and melting behavior. Ideal basicity improves fluidity, narrowing the CZ. Gangue content, high impurity content leads to wider melting range and thicker CZ. Example. A pellet with Ts equals to 1150 degrees Celsius and Tm equals to 1400 degrees Celsius gives CZ thickness equals to 250 degrees Celsius, temperature-wise. A sinter with Ts equals to 1200 degrees Celsius and Tm equals to 1350 degrees Celsius gives a narrower CZ 150 degrees Celsius, more desirable. Next, burden layering and distribution. The physical distribution of materials inside the furnace, including layer thickness, particle size, and distribution pattern, has a direct effect on cohesive zone shape and thickness. Important considerations. Layering of coke and iron-bearing materials affects heat transfer and melting rate. Fine particles in sinter ore pellets make log voids, reducing permeability and delaying melting thicker CZ. Segregation or uneven distribution can lead to asymmetric CZ shapes and varying local thickness. Type and quality of iron ore. Different iron ore burden types exhibit varying softening and melting behaviors. Sinter generally has better softening behavior due to porous structure, but may have a wider melting range, contributing to a moderately thick CZ. Pellets. High iron content, uniform size, high strength, but tends to have a sharp melting point, forming a thinner CZ if controlled well. Lump ore may disintegrate at high temperature, forming fines that reduce permeability. Can lead to irregular and thicker cohesive zones. Optimized burden mix, for example, sinter plus pellets in right ratio, can help maintain a balanced and thin cohesive zone. Next, coke quality and reactivity. The coke in the cohesive zone serves multiple roles. Provides mechanical support to the softening burden. Acts as a gas pathway. Supplies carbon for reduction and carburization. KY coke properties affecting CZ. Coke strength after reaction, CSR. High CSR resists degradation under high temperatures, maintains permeability narrower CZ. Coke reactivity index, Cre affects how quickly coke reacts and degrades. Size and uniformity. Uneven coke size can result in poor burden support and irregular heat distribution. Thicker CZ. POR coke quality leads to coke collapse or fines formation. Reduces gas permeability, delaying melting. Increased CZ thickness. Slag composition and behavior. During softening and melting, slag forms from gangue minerals and fluxes. The properties of slag affect how quickly the burden melts and flows down. Low melting point slag forms more readily, accelerates dripping. Results in a thinner cohesive zone. Viscous or high melting point slag hinders melting and flow. Causes burden material to remain longer in semi-molten state, increasing CZ thickness. Influencing components. SiO2 Al2O3 increase slag viscosity and melting point. MgO CaO improve fluidity and reduce slag melting temperature. Next, operating temperature profile. The thermal profile of the blast furnace, particularly in the lower shaft, determines how quickly burden materials reach their softening and melting points. Higher temperatures accelerate softening and melting. Promote faster transition through the CZ thinner cohesive zone. Lower temperatures or heat losses delay melting. Cause burden to remain in plastic state longer. Thicker CZ. Proper control of blast temperature, typically 1200 to 1300 degrees Celsius, and oxygen enrichment is essential to maintaining correct thermal gradients and CZ thickness. Next, gas flow and permeability. The upward flow of reducing gases through the furnace affects heat transfer and burden heating. Poor gas permeability slows heat transfer to burden. Delays melting, increases softening range. Thicker cohesive zone. Uniform gas flow, even heating and consistent melting. Promotes a uniform and thin cohesive zone. Localized gas channeling can cause non-uniform thickness of the cohesive zone across the furnace cross-section. Burden descent speed and productivity. The speed at which burden descends affects residence time in the softening melting range. Faster descent may not allow sufficient time for full melting. Leads to thicker cohesive zone if dripping is delayed. Slower descent promotes longer residence time in high temperature zones. Can narrow the CZ, but risks overheating or slag buildup if uncontrolled. High productivity furnaces require precise control of burden descent to avoid thick CZs. Next, furnace geometry and design. The design of the blast furnace, particularly the Bosch angle and hearth diameter, influences heat distribution, gas flow pattern, burden descent trajectory. Wide Bosch promotes better gas-solid contact, supports thinner and more uniform CZ. Narrow Bosch or irregular lining can lead to uneven temperature profile. Results in irregular and thicker cohesive zone. Summary: key factors and their effect on CZ thickness. Wider softening melting range of burden increases CZ thickness. Poor burden distribution or fine segregation increases CZ thickness. High gangue or alumina content increases CZ thickness. High CSR coke with good size reduces CZ thickness. Low melting slag components CaO reduces CZ thickness. High blast temperature or oxygen enrichment reduces CZ thickness. Poor gas permeability increases CZ thickness. Fast burden descent. Increases CZ thickness. Uniform furnace geometry and stable operation. Promotes thin and uniform CZ. Conclusion. The cohesive zone thickness in a blast furnace is a function of both material properties and operational parameters. Optimizing burden quality, coke strength, slag chemistry, gas flow, and thermal profile is essential to controlling CZ thickness. A thin, stable, and uniformly distributed cohesive zone is crucial for ensuring efficient gas-solid interaction, smooth burden descent, high productivity, low fuel consumption, operational stability. Understanding and managing the factors affecting cohesive zone thickness is therefore fundamental to modern blast furnace optimization.